So in this class, I will solve two problems on support reactions, examination problems, VTU. The first problem states like this. It is June 2017 question paper problem. So here is asked the support reactions for this beam. So this beam, you can see here, one end is hinged, one end is on roller, and it has got an overhang portion here. So it carries a concentrated load of 20 kN at the free end of the overhang, a UDL of 10 kN per meter in the overhang portion, in this portion, and it carries a triangular load like this, uniformly varying load, whose intensity varies from 0 to 60. So this is 16 kN per meter, and it carries a concentrated load of 30 kN. This is A, this is B. So A and B, they are the supports. A is a roller support, B is a hinge support. The distances, and this has given C, I will take this as B, this as G. Now the distances are given like this. This is 2 meters, 6 meters, 2 meters, 2 meters. This is the given problem. So we have to find the reactions here. So find the support reactions. So here you can see that one support is roller, where you can have only one reaction, normal to the roller. And another one is hinge, B is a hinge, where you can, there is a possibility of two supports, two reactions, one is horizontal and one is vertical. But here in this problem, there is no horizontal load or there is no inclined load. If there is inclined load, then it will have a horizontal reaction also to resist the horizontal component of the inclined load. Here that inclined load is not there, therefore we can have only two reactions here. One is RA, another is RB like this. Both are vertical reactions. So only two equilibrium equations are enough to solve this problem. So reactions are only RA and RB. So two equilibrium equations. So one corresponding to the vertical forces, that is sigma Fi0, and another one which is respect to the moment, that is sigma M0. Either you can take sigma Ma0 or sigma Mb0. Now using these two equilibrium equations, you can solve for the reactions. Now the first step is to write the free body diagram of the beam, the FBD of beam. So by removing the support and replacing the supports with respective reactions, and also by transforming or converting this UDL and UVL into concentrated load, you can apply all the external loads, and then you will get the FBD. So FBD I will just write like this. So this is C, this is A, then this is D, E, B. So at A you have a reaction RA, and at B also we have vertical reaction RB. Now the corresponding loads here are 20 kN concentrated load at the end C. Then you have a UDL here from C to A. This UDL can be converted to a concentrated load acting at the midpoint, and the value of the concentrated load is intensity multiplied distance, 10 into 2, 20. So the 20 kN will be acting at the midpoint of CA. So I will take this as 10 into 2, 20 kN. Midpoint of midpoint of CA is 1 meter from C, because CA is 2 meters. Now this UVL also, triangle also, you have to convert into concentrated load. So its concentrated load value is equal, concentrated load is half into base into height, area of the triangle. So it is half into 6 into 60, which is 180 kN. It will be acting at the CG of the triangle. So CG of the triangle will be here. So here we have to take the load. So load is 180 kilonewton acting at the centroid or center of gravity of the triangle, which lies at a distance of 2/3 from A of the base from A or 1/3 from D. From the end it is 1/3. From the apex it is 2/3. So 2/3 of base is 4 meters. 1/3 of base is 2 meters. Now that means this G, point G will be here. So you have to take that point G at a distance of 4 meters from A. So this is very important, and from D it is 2 meters. So this is 180 kilonewton. 180 kilonewton concentrated load. Then you have a concentrated load acting at E that is given in the problem itself, 30 kilonewton. So now this is the free body diagram. So DE is 2 meters and EB is also 2 meters. So distances it should be correct. So you should write correct. So 1 meter, 1 meter, then 4 meters, 2 meters, then 2 meter, 2 meters. So total span of the beam is total span here is 12 meters. Total span is 12 meters. Now we have to apply the equilibrium equations. These two are the equilibrium equations. Let me apply the moment equation first. Sigma mv is equal to 0 you can take. So same convention is when you are applying moment equation, clockwise moments we are going to take positive, anti-clockwise negative. Now I am here at B. Take the moments of all these forces including reaction about the point B. So moment is force multiplied by the perpendicular distance. So it is giving an anti-clockwise moment. 20 kilonewton is giving an anti-clockwise moment minus 20 into distance is 12 meters. Okay, then 20 kilonewton, this 20 kilonewton is also giving anti-clockwise moment minus 20 into distance is 11 meters from B. You have to take distance from B. Then you have RA. So this RA is giving a clockwise moment. So plus RA into distance is 10 meters from B. Then you have to take this load acting at G centroid, that is 180, which is giving anti-clockwise moment minus 180 multiplied by distance is 6 meters. Then 30 kilonewton, that is also giving anti-clockwise moment minus 30 into 2 meters. This RB does not have any moment about B because the line of action passes through B. So this should be equal to 0. Now this is the moment equation. So minus 20 into 12 minus 20 into 11, then plus RA into 10 minus 180 into 6 minus 30 into 2. So this equation should write correctly. See here only one unknown is there. RA is the only one unknown. So you can solve for that RA. So 10 RA is equal to, so all these become positive if you bring to RHS. So this becomes 240. This becomes 220. So 240 plus 220. This becomes plus 180 into 6 plus 60, 30 into 2. This becomes 1600. Therefore, RA is equal to 1600 divided by 10, 160 kilonewton. You have got positive value, that means the assumed direction of RA is correct, it is upwards. Now, using the second equation, you can find out the another reaction. Sigma Fy is equal to 0, upward positive, downward negative for the vertical force. So upward forces are RA and RB. So RA plus RB, others are negative. Downward forces minus 20, minus 180, minus 30 is equal to 0. Or in other words, RA plus RB is equal to 40, 220, 250. Or since you know the value of RA, RB will be 250 minus RA. It is 250 minus 160, which is 90 kilonewton. So that is also positive. So that means your assumed direction is correct. So like this, we have to find the reaction. So RA and RB we got by using the two equations of equilibrium. Now the second problem is also examination problem. So I will take that problem. Second problem, it runs like this. It is a model question paper problem. Model question paper problem of VTU. So here he has given the beam like this. So there is a roller end, there is a hinge end here at A, and at B you have a roller end, roller support, inclined roller. So the roller is inclined at an angle of 40 degrees. 40 degrees with this angle is 40 degree. Then next, this carries beam AB carries a UDL of 20 kN per meter up to 3 meters. So this is 20 kN per meter up to a length of 3 meters. Then it carries a concentrated load here, 20 kN. Then a triangular load for a length of 4 meters. For a length of 4 meters, it carries a triangular load like this. Intensity varies from 0 to 30. So this is 30 kN per meter. So AB is the beam. So I will just take this as C. So totally there are 3 loads: 20 kN per meter UDL, 20 kN concentrated load, and 30 kN per 0 to 30 kN per meter, that is triangular. Now here the thing here is how many reactions will be there, that you have to see. So in this case there is a hinge support. Normally in general you have 2 reactions here, one roller support, one reaction normal to the roller. So totally 3 reactions will be there here. So in this problem, even though inclined load is not there, since the roller is inclined, it will have horizontal reaction, because the horizontal component of the reaction at roller will be there. So that should be adjusted with the horizontal reaction that is going to develop at A. So please note the difference here, because even though load is not inclined, since the roller support is inclined, we will be having the horizontal component of the reaction at the hinge end. So that is why I have taken this problem. Now the first step is to first identify the reactions here at the supports. You have, I will take HA like this, VA like initially you can assume any direction, horizontal, vertical, left, right. Finally, after solving the equilibrium equation, if you get the value positive, the assumed direction of the reaction is correct. If you get negative, it is opposite direction. That's all. Here in the roller, so you will be having only one reaction RB, which is developing a normal to this roller. So this I will resolve into 2 components like this. Since this is 40, this angle becomes 50. So very important, 90 minus 40. So the angle made by RB with horizontal will be 50. Therefore, the horizontal component will be RB cos 50. Vertical component will be RB sin 50. So you will be having 2 components of the reaction, because the reaction itself is inclined with respect to the global x and y axis. Now we will have to use once again all the 3 equations we have to use here, because there is a horizontal component also for the reaction at the hinge end. So you have to use all the 3 equilibrium equations. So I will write here, there are 3 reactions in this case. So the reactions being HA, VA and RB. Of course, RA can be found out, resultant reaction at the hinge can be found out by using this formula, HA square plus VA square W, and the angle made by that RA with respect to horizontal can be found out using tan inverse of VA by HA modulus. So this is the way we have to use. So we have to use all the 3 equilibrium equations here to So the first equation I am going to use sigma fx 0, forces acting towards right positive, left negative. If you observe this, so anyway, let me write the free body diagram. Then I will apply this equation, free body diagram of the beam. So AB is the beam. So we have to convert that UDL and triangular load into equivalent concentrated load. So at A you have two reactions, at A we are like this. At B I will take the resolved components of the reaction. RB sin 50 vertical reaction, RB cos 50 horizontal reaction. Then of course I will convert this to equivalent point load. So point load will be 20 into 360 kN acting at the midpoint. So I have to take here 60 kN acting at midpoint means acting at 1.5 meters distance from the point A, support A. Then at C is here. So you have another concentrated load given 20 kN. So this distance is 1.5 from. So this side will take it as B. From B to C it is 1.5. Then here this equivalent concentrated load acts at the CG or the center of the triangle. So it will be at a distance of 2/3 from the vertex. So that is 2/3 of the base. 8/3. 8/3 is 2.67 meters, and this will be then automatically 1.33. Total will be 4, So that means here from C to G, it is 2.67 meters, and remaining 1.33 is this. That is from G to B. Now this load, equal point load, will be area of the triangle, which is half into base into height, half into 4 into 30. Half into 4 into 30, which comes out to be 60 kN. So equivalent concentrated load is 60 kN. Now this is the free body diagram of the beam. Now let me apply the three equations one by one. Sigma fx is equal to 0, force acting towards right positive, left negative. So HA minus RB cos 50 is equal to 0. So you cannot solve this because there are two unknowns. Solve this as equation 1. Second equation is sigma fy is equal to 0, upward positive, downward negative. So VA plus RB sin 50, both are positive because acting upwards, others are negative. Minus 60, minus 20, minus 60 is equal to 0. Or you can write VA plus RB sin 60, sin 50 is equal to 100. So this is equation 2. Second equation. Now the third equation, moment equation, either you can take sigma MA0 or sigma MB0. Okay, let me take sigma MA is equal to 0, clockwise positive, anti-clockwise negative. Now here, both HA and VA, they don't have any moment about A because the lines of action passes through A. There is no perpendicular distance. This gives a clockwise moment 60 into 1.5 positive. 20 into 3 positive clockwise, then plus 60 into, this is 3 plus 2.67, 5.67, then this RB sin 60 gives a negative anti-clockwise moment, negative RB sin 60 into total distance is 4 plus 3, 7 meters from A. This RB cos 60 does not have any moment about A because the line of action passes through A and the linear arrow is 0. So this is equal to 0. Now from this you can easily get the value of RB. So RB is equal to, you can bring all these, this RB sin 60 into 7 you can bring to RHS, it becomes positive. This I have to simplify. 60 into 1.5 is 90 plus 20 into 3 is 60. Plus 60 into 5.67. So this is the LHS value we are going to get. This divided by 7 divided by sin 60, that gives the value of RB, which comes out to be 80.862. 80.862 kilonewton. So positive value got, that means your assumed direction of RB is correct. Now once you get this RB value, substitute in equation 2 to get the value of VA, and substitute in equation 1 to get the value of HA. So substituting in 1 for RB, so HA is equal to RB cos 50, so it is 80.862 into cos 50 degrees, which is cos 50 is equal to 51.977, or you can take 52 kilonewton. Of course, this value is positive, that means your assumed direction of HA is correct. Then substituting the value of RB in second equation, you will get the value of VA. So substituting in 2, so VA is equal to 100 minus RB sin 50. 100 minus, oh sorry, this is not 100, this is 140, 60, 20, 140 minus RB sin 50, that is 140 minus RB is 80.862 into sin 50. So if you simplify that, you will get 140 minus of 80.862 into sin 50, which is equal to 78.056. 78.056 kilonewton. Positive value got, that means whatever direction you have assumed like this for RB, for VA, of course it is like this. Here of course RB is like this. Yes. So same direction, that is same. So now once you get VA and HA, you can find out the resultant reaction RA using this root of HA square plus VA square, which comes out to be HA is 52, so 52 square plus 78.056 square under root, so 93.79 kilonewton. So the direction of RA will be, now you can fix it, because HA is like this and VA is like this, so definitely the direction of RA will be like this. This is RA, because HA is towards right, VA is upwards, this is RA, that is first quadrant we can say. So angle made by RA with respect to horizontal will be tan inverse of alpha, will be tan inverse of modulus VA by HA, which comes out to be tan inverse of 78.056 divided by 52. So it comes out to be 56.33 degrees. This is the angle. So this is how you are going to get the reactions. Once you get the reactions, you can always show the reactions in the diagram. Finally, so only reactions I am going to show here. So AB is the beam. So at B you have RB is equal to 80.862 kilonewton, taking an angle of 50 degrees with horizontal. At A you have RA like this. So I am going to show only RA, which is equal to, 93.79 kilometer, which makes an angle of alpha, which is 56.3 degrees. So this is how we can find out the reactions using the three equations of equilibrium. So in this problem we can observe that even though there is no inclined load, since the support is inclined, so you will be having all the three reactions, even horizontal reaction at the hinge also will develop.